Eclipse series. So we're super excited about today's talk. And then we have one more, the first Friday of April, which will be April 5th. Lou Mayo will be giving a presentation on alignments within the solar system. So eclipses and occultations and things like that. That is the weekend of the Total Solar Eclipse Festival. So that will be the Friday, which will be beginning of the whole weekend of events. The website to keep an eye on is eclipse.siu.edu. It has all the information on the eclipse. It has all the information on the festival, the talks, the activities, the stadium show, everything. Okay, as you're talking to other members of the public, please be sure to help us spread the word that there's 2 events on campus that require tickets. Everything else is free. So there's tickets to get into the Comic-Con. SIU students get in with their ID. There are tickets for the stadium show. There are free student tickets for SIU students. Everything else on campus for the whole festival, it's free for everyone. So please join us. We have an expo, we have an arts and crafts festival, we have speakers, there's a concert in Carbondale. There's all sorts of amazing, cool things going on that weekend. Okay, all that information is on eclipse.siu.edu. All right, it is my great privilege to introduce you to today's speaker. This is Dr. Rawafi. He is an astrophysicist with the Applied Physics Lab at Johns Hopkins University. He is the lead project scientist for the Parker Solar Probe, which means if you have questions about Parker Solar Probe, he's going to know the answers, right? So this is going to be very fun. He got his Ph.D. from the University of Paris, and then he worked at the Max Planck Institute in Germany, which for those of us in physics is a very big, very famous institute. And then he worked for the National Solar Observatory in the US. Very involved in solar science, very involved in the last eclipse and the upcoming eclipse. So then he joined the Applied Physics Lab at Johns Hopkins. Okay, and so he's going to share his amazing spacecraft with us and all the very cool things that it is doing. We will definitely have time at the end for questions. So please think of things to ask him because he's here for us. And the floor is yours, sir.
Thank you so much. And it's really great pleasure to be with you. And thank you so much for the invitation. Anyway, it is, I wish it was in person because in person is always better in some ways. But anyway, so it's good. So I'm going to talk to you about the Parker Solar Probe and what we have achieved so far. But the title I put there, it's 5-year exploration of the near solar environment. It should be probably extreme exploration, trailblazing with Parker Solar Probe around the sun or something like that, because Parker Solar Probe is by design a mission of extremes. We go closest to a star ever. That is a huge achievement for all of us. And by the way, so we will have the eclipse on April 8th, but that's not the end of it. On the eve of Christmas of this year, we will be hitting the closest approach of a human-made object to a star ever. And that is actually one Parker Solar Probe fly closest to the sun ever, which will be 3.8 million miles from the surface of the sun. And that 3.8 million miles might sound like a huge number, but it is only 4% of this, the sun-Earth distance. So we are flying within the solar corona that we will see during the total solar eclipse in April 8th. So, okay, talking about solar eclipses. So what is a total solar eclipse? To me, well, it's a celestial event. It's one of the most captivating events that we can witness along the path of totality. We will see the corona like with the naked eye, like we can never ever see it because of the brightness of the solar disk. And it's moving. And if you go to the deep in history, people interpreted solar eclipse in different ways. Some of them use it for religious purposes, for even for economic and societal purposes as well. But anyway, solar eclipses are way more than that. We are talking about science here. And the way solar eclipses serve science there are things that we've done over the centuries with solar eclipses that nobody talks about now, and it's a little bit unfortunate, but they have been done. So okay, I assume you all guessed what this picture is from. This is the first picture from the James Webb telescope, and you might wonder why I'm showing a deep field of the universe with plenty of galaxies and stellar systems. What do they have to do with eclipses? Okay, let me tell you. You see all this arcing structure, these small arcs here, they are almost everywhere. That is the gravity lensing. Basically, when you have a massive star or even a galaxy, they are so massive, they will bend the light that are of sources behind them. And then what we see the sources that are on the background, we see them in the form of arcs, simply because the light was bent by the huge gravity of either the stars or the galaxies. So again, why I'm showing this, what does this have to do with solar eclipses? The first one who theorized the existence of this gravity lensing is Albert Einstein, and with his relativity theory. And guess what? Solar eclipses were the first experiment used to verify the theory of Albert Einstein, and that was in 1919 during total solar eclipse. There are several expeditions in different places just to try to verify whether Einstein was correct or not. And guess what? He was. And this is the New York Times. That is also the Illustrated London News and some other journals as well. It was, in a way, a triumph for all humanity, for all the science that we are doing, and proving the relativity to be true in that sense. It's a huge thing. And guess what? We used a total solar eclipse for it. I can go on and on about what we used solar eclipses for, but it's just an amazing event that we enjoy. It's so fascinating, but also we use it for science and all that. So, okay, moving now to the solar eclipse of August 7, 1869. There are two American astronomers. One of them, by the way, is in the military. Harkness is in the military. The other one is a civilian. They were both went to Iowa to observe this total solar eclipse, and they were not far apart. And independently, they made exactly the same observation. And that observation, by the way, this is actually the true picture of one of the, I believe it's the Des Moines experiment. And you can see it there. There are the folks who are doing the experiment, but there are other folks as well who show up just to see the eclipse. So what we learned from that experiment, so both of them, Young and Harkness, observed the same emission from the solar corona. It is in the green part of the spectrum, and to this day we call it the green line, by the way. It is at 5303 angstrom, but the problem with it that nobody knew what was the chemical element that was responsible for that emission. And that mystery lasted for 70 years. And nobody knew what was it. And by the way, along the way, people invented even a hypothetical new chemical element. They called it coronium. But after that, it was proven wrong. It was not true. So by the late 30s, early 40s, Grotrian and Edlin, who are famous, one of them is a theoretician, the other one is experimentalist. They actually showed that the green line is emitted by iron ionized 13 times. You basically take an atom of iron, has 26 electrons, strip 13 electrons out of the 26, and you get that ion. And they proved it because the laboratory spectroscopy was developed to the point that we can have a plasmas at very high temperatures. But the issue that the iron 13 plus can exist only in multi-million degree plasma. And by solving the mystery of the green line, we actually discovered a much bigger problem, astrophysical problem. The fact that the iron 13 plus exists in the solar corona means that the solar corona is multi-million degree hot. And that is so puzzling and enigmatic. And because we know when we look at the solar surface that we see with the naked eye, the temperature of the plasma is about 6,000 to 10,000 degrees. And over very short distances, we are talking about a few thousands kilometers. The temperature of the gas or the plasma will jump to more than 2 million degrees Fahrenheit. And that is so counterintuitive. So to this day, we don't really have a full understanding what causes the corona to be much hotter than the solar surface. And that is 300 times hotter than the solar surface. And so that's the birth of the coronal heating. By the way, the coronal heating, I will come back to it a little later. That's one of the primary objectives of Parker Solar Probe. Let me go back to eclipses again. So in 2017, we have the total solar eclipse crossing the continental US from the northwest to the southeast. And the 2024 eclipse, it's the other way around, the other diagonal. And they cross, the two paths across here. And this is exactly where the discovery of the coronal heating was made. That is the path of totality of the eclipse of 1869 passed through Iowa, and the two experiments, one of them was at the center here, the other one was around here. So we are just, I believe it's something like 200 or 300 miles away from where that major discovery was done. To me, when I saw this graphic, it was like, yeah, we had one solar eclipse before the launch of Parker Solar Probe, another solar eclipse 5 years later. It's basically like these two solar eclipses, they are telling us, you better close on this major solar phenomenon that you want to explain, that are the coronal heating, the solar wind, and energetic particles that I will talk about in a little bit. So what is the coronal heating? I already almost told you everything about it. When you look at the temperature as a function of altitude, as you move out from the solar surface out, we go from a few thousand degrees to multi-million degrees. And as I said, it was discovered in the late 30s, early 40s. And to this day, we are needing Parker Solar Probe to tell us what is going on there. We have been observing the sun and the solar corona for decades now, but we cannot really understand what is going on. So we need a spacecraft to get very close to the sun to tell us what is causing all this heating and all these manifestations that we are seeing there. So the other phenomenon, which is basically the other side of the coin to the coronal heating, it's the acceleration of the solar wind. So the solar wind is a flow of particles that are electrons, protons, alphas, and heavy ions. They stream away from the sun to fill the whole hemisphere. That is the solar wind. And the issue with the solar wind, again, then when you look very low down, close to the solar surface, the speed of these particles is pretty low. We are talking probably at 5 to 10 kilometers per second. But over a very short distance, they start flying at velocities going from 300 to 800 kilometers per second. That is, okay, 800 kilometers per second is equivalent to something close to 2 million miles per hour. So to put that in perspective, if you are flying at that speed, 2 million miles per hour, you can actually make the flight from Earth to the moon in less than 20 seconds. That's how the solar wind is, how this flows fast. And again, where the particles are getting the energy from to be accelerated so fast, we don't really know. So basically, to explain the coronal heating and the acceleration of the wind, what we are looking for are sources of energy that the particles can get what they need to be hot and fast. And that's not all. The sun is a magnetized star, and by nature, a magnetized star is active, is violent, and it is changing all the time. And every now and then, you will see big explosions on the sun, like flares and coronal mass ejections. And whenever you have one of these events, in particular the big ones, you get a certain population of these particles to be accelerated to almost the speed of light. We call this the solar cosmic rays, or we call them also solar energetic particles. And these particles are are very hazardous to space equipment, to humans in space. If we are thinking to have permanent presence on the moon, we have women and men up there on the moon. So we have to be very watchful for this, for these particles. But also for our space equipment there, whenever we have a big event like that, they can actually damage the electronics. And when they are severe enough, they first of all cause the spectacle of the aurorae that we can see on the North Pole and the South Pole of the Earth, but also their effect can reach us on the ground here. And you might be aware of the power outage of March 1989, where the northeast of the US and Canada had a blackout for many, many hours. And that's actually was caused by a solar storm that is caused by an explosion of the sun. So these are the three main objectives of the Parker Solar Probe mission. But if you think of it, Parker Solar Probe is way more than that. And why I'm saying that? Because we are venturing into a region of space that we never visited before. And in some ways, when you are going into a new place, whatever observation you make is like, it's a new discovery for you. And Parker Solar Probe is also venturing into this region, this mysterious region close to the sun that we never visited before. And what we expect, whatever measurements we make, is a potential discovery. And that is exactly what we are learning from the data. So, so to put it just in 2 words, we have been observing the sun for decades now, but to solve these big problems, we needed a spacecraft to fly as close as possible to the sun and give us some data to tell us what is the action taking place there that gets the plasma hot, fast, and also accelerate these hazardous energetic particles there. So that is Parker Solar Probe. And you might think that the idea of sending a probe to fly closest to the sun is a new one. Actually, it's not. It is a very old one, and it dates back to 1958. Scientists back then were thinking, yeah, we need a spacecraft to fly within the orbit of Mercury to tell us, yeah, what are the particles and fields there. And NASA tried multiple times to implement this mission, the Parker Solar Probe. Well, no, back then it was not called Parker Solar Probe; it called other names. So, but they did not. All this attempt didn't really materialize. They did not succeed for multiple reasons. Either the mission was too costly, or I think the main reason that is it's almost certain we did not really have the technology to fly a spacecraft very close to a star and fly it in a safe manner. Because when you are close to the sun, if you are not watchful for your spacecraft, you will lose it like this, because the environment is so harsh. The radiation coming from the sun is so intense, and your spacecraft will just fry in no time at all. So this is Parker Solar Probe, and Parker Solar Probe is not really a gigantic spacecraft. It's not very small. It's not huge. It is, you know, from the top here to the bottom here, we are talking about something like 3 meters. That's the height of Parker Solar Probe. If you add the boom to it, that will go to 5 meters. But the main body of the spacecraft is basically 3 meters. So what was the thing that, let me talk a little bit about the payload that we have, and after that I'll talk what was the technology that enabled the mission to be implemented. So we have 4 instrument suites. The first one is the imager. It's this box here, you see it around here. And that's a white light imager. Obviously, we cannot look directly at the sun because the instruments will not survive. So with these imagers, we are basically looking to the side of the sun, and we see the solar wind accelerating from the edge of the sun all the way past Earth. So that's a white light imager. Then we have the electric the fields, which have 5 electric antennas. 4 of them are mounted just behind the thermal shield. I will talk about the thermal shield in a minute. So that's the 4 electric antennas. There is a 5th one, which is on the boom here. So there are 5 electric antennas, but also we have these magnetometers here. There is one here, and one at the tip of the boom. That's the field suite. The field suite will measure magnetic fields, electric fields, densities, temperatures, waves, radio emissions, and all sorts of fluctuations in the solar wind. And then we have different sensors, sweep that will measure the thermal solar wind. We have this sensor here. There is another one on the other side of the spacecraft, but there is also another instrument that is mounted just next to the TPS. It's on the other side that we cannot see it from here. And that small instrument, which is a Faraday cap, together with these electric antennas, they are the only sensors that are exposed to the full solar environment. All the rest of the payload resides on the shade of the TPS, on the main body of the spacecraft or on the boom, which are always protected by the TPS. The fourth suite, which is the energetic particle suite, that will measure these hazardous energetic particles. It's ESIS. Now, historically, when scientists and engineers were thinking about this mission, we always thought, okay, in order to get so close to the sun, we need to launch the spacecraft all the way out to Jupiter, have a gravity assist to get out of the ecliptic, and then have a deep dive toward the sun. And that deep dive is very, very close to the sun. We are talking about a few solar radii from the sun. And that mission, the spacecraft will be flying so fast there that basically you will have something like 14, 15 hours worth of measurements. That's all you will get out of the mission. And that's actually what drove the mission so costly and didn't really materialize into a real mission. So, but back in 2006, 7, our engineers at EPL came up with a new idea to implement the mission. Instead of using Jupiter to get a deep dive into the solar atmosphere, they said, you know what, we can use Venus multiple times. And every time we fly by Venus, basically we slow down the spacecraft a tiny bit. It's a gravity assist, but the spacecraft loses momentum to the planet. It's so tiny, so it's very small. But for the spacecraft, it's sufficient to have a deep dive toward the sun. And flying by Venus 7 times over 7 years, basically we get where we want to be. The advantage of this approach is that you get a much longer mission. We are talking about a prime mission of 7 years. But eventually the mission will continue after that because the spacecraft is pretty healthy. And so far we did 5 years and a half. We still have 1.5 years into the prime mission. But the culmination of all of this is this date, the eve of Christmas 2024, when Parker Solar Probe hit the closest point ever to the sun, that is 9.86 solar radii from the surface, or 3.8 million miles from the, the 9.86 is from the center, but the 3.8 million miles is from the solar surface. So what is the science we want to address with Parker Solar Probe? I talked about the coronal heating and the solar wind. To me, in a way, they are in some ways the same phenomenon. If we explain one, we explain the other one. So there are 3 main questions about the heating and the acceleration of the plasma. So the first one is, what are the physical processes that give birth to the different regimes of the solar wind? So we have the fast solar wind that is flying at velocities between 500 and 800 kilometers per second. We know it's coming from coronal holes, and that's pretty well established. We know that. We have also the slow solar wind, which is flying at velocities between something like 200 up to 500 kilometers per second. The source of it is not very clear. It's pretty controversial where it is coming from exactly. The other question about the solar wind, we know when we measure it around 1 AU around Earth, it looks like a homogeneous flow. But the question is, at the source, when it is born lower down here at the base of the corona, is it still a continuous flow or it is intermittent? By intermittent, I mean it is based on individual events. Because if it is one scenario or the other, the physics is totally different. So answering this question is so fundamental to understand the solar wind. The third one is obviously, it's the big elephant in the room, is okay, you create your solar wind here, but the sun have a huge gravity pull. And the big question is, how can you get the wind to escape the gravity of the sun? Basically, what keeps the solar wind being accelerated as it is moving away from the sun and not falling back? And this is one of the big questions that we have been trying to answer for the last 6 decades, since basically the discovery of the solar wind in the early 60s. Okay, when Parker Solar Probe flew very close to the sun, it observed something that is pretty original. What we saw there, we saw kinks in the magnetic field. Basically, the magnetic field rotates over itself all the way back to the sun and out again. It forms what we call S-shapes or reversals or magnetic switchbacks. When you look at them here in the inset here, in red, we have that is the magnitude of the magnetic field. In black, this is the radial component of the field. You see it going from 100 nanotesla on this side to almost minus 100 nanotesla on here, and after that it goes back to the original configuration, which is the 100 nanotesla again. And look what it does to the dynamics of the plasma. Here, when we are outside of the switchback, we have a slow solar wind, about 300 kilometers per second. We enter this structure and we jump to a fast solar wind. And when we get out of it again, we go back to a solar wind again. So when we saw this, we said, oh, wow, this might be actually the smoking gun we are looking at. But the issue with it is that when we got close to the sun, we saw a gazillion of them. They are everywhere. And we have never seen that before. And just for history, when we got this data, actually, we got it in 2018. It was a Tuesday, and it was the American Geophysical Union. And on Thursday, we were supposed to share this data with the public. So, but when you looked at this data, it was so shocking to us. The first thing we thought about was something is wrong with the instrument. And I still remember somebody of the audience was saying something like, for God's sake, we don't need this now. I mean, if you are looking for this mission for over 6 decades, and the first thing you get is something wrong with your instrument, it's so bad. In particular, that you have only 2 days that you cannot do anything to your instrument to rectify if there is something wrong with it. But the fact of the matter is, it took us about 10 to 15 minutes to figure out, actually, there is nothing wrong with the instrument. What we are observing is something totally new that we have not seen before, and what we are seeing is new physics that we are seeing manifesting in the solar wind and the solar corona. And this is exactly the very first plot, by the way, we saw. So when we are far away from the sun, we are used to these low amplitude fluctuations here. But when we got close to the sun, we saw this. And that's actually what told us, yeah, there might be something wrong there. So, but anyway, everything is fine. Everything is what we are seeing. What actually we're looking at is what we hoped for a long time, is something new that it's basically a paradigm shifting thing. And we got it from this data set. And then after that, came the series of questions about these switchbacks. So where do they fall? Where do they come from? How do they evolve? And what is their contribution to the acceleration and the heating of the solar wind? Here we are started talking about the role of the structure in explaining the coronal heating and the acceleration of the wind. We are talking serious physics here. And we keep looking at them, and there are many things we discover about them. First of all, these things are not random at all. They are very well organized. So the sun is doing something in an organized way, which is another hint. And by organized, this is what I mean. They don't really come as singular events or things like that. No, actually, they come in groups. We call them patches. A patch is like this, one of these here. You have plenty of switchbacks in the middle, but in the edges here, there is not much of them. You move out of it and you get another patch like this one here or this one here. So in a way, the sun is producing these switchbacks in a very organized manner. And that is a hint to us. These patches might be actually reminiscent of the physical processes that are driving the solar wind to start with. And that is a hint that we never had before. There is another thing also that we talk about. It's really intrinsic property to plasma, whether it's about the the amount of fluctuations of the plasma, and we are talking about here fluctuations in the magnetic field and the velocity. And when you have this correlation between the field and the velocity, they are highly correlated. We talk about the wind being galvanic, meaning the fluctuations are dominant in that plasma. And when we observe the solar wind far away from the sun, we are talking about the fast solar wind is always galvanic. The slow solar wind is typically not galvanic. But the shocking thing, when we got close to the sun, everything is galvanic regardless of the speed of the wind. And there again, it's a new thing that we have not seen before. So we started looking at images of the sun, trying to explain, okay, what is going on there? What's the deal? What is creating these switch paths? And when you take this, by the way, this is a movie playing from the Solar Dynamic Observatory, that is another NASA mission. And we were interested in the off-limb here, the solar corona, and trying to see if there is anything that can relate to these switch paths. And when you look at the raw images, you basically don't see anything. You see only haze that is around there. But the fact of the matter, when you filter your images really well, you start seeing the real stuff. And by the real stuff is basically wherever you look, you will have very tiny jets that are propelling hot plasma into the solar corona. And let me go to the next one, the next movie. It's a zoom on one of the poles. And when you look at them, you get the impression that you are seeing a flow rising from the base of the corona all the way up. And the question came to us, well, is this solar wind? Are we seeing the solar wind being born? And by the way, these tiny jets, we call them jetlets because they are very small. And the nice thing about them, they are everywhere. Wherever you look, whether on the poles, elsewhere, they are everywhere. And that is actually another properties of the solar wind. The solar wind is a global phenomenon. So the source of it has to be global as well. And we are looking at something that is occurring all the time and everywhere, exactly like the solar wind. And now we started talking about, now we are seeing what causes solar wind and what causes it to be hot in the first place. So we looked a little further. What is all this about? And what we saw there is when you look at the very high resolution magnetic fields from the sun, you see what we call this salt and pepper. It looks chaotic, and the fact of the matter, and when you see the evolution in particular, you see basically the black and white, which are the different polarities of the magnetic field, canceling each other's. And that's where what we are looking for. Because this cancellation is basically the magnetic field is reflecting there. There is a connection there. And that's what releases the energy from the magnetic field to the plasma in the form of heat and speed. So the jetting we are seeing, what I showed earlier, is just a manifestation of the connection that we are seeing here. And when you look at very small scale, it is all over the place. So now, in a way, we are really closing in and to explaining this big problems that are the column heating, the acceleration of the wind. And this is actually what you get when you go bold and you invest into a mission that is a daring mission, I would say, like Parker Solar Probe. You start solving problems. And so again, earlier I talked about the big explosions on the sun, and Parker Solar Probe, when it gets close to the sun, we cannot really shield it from this event. So, but we designed it in a way that it can withstand this big explosions. And on September 5th of 2022, the sun launched one of these colossal coronal mass ejections. It's so big that it was flying at more than 2,500 kilometers per second. And guess what? Parker Solar Probe was so close to the sun, it was at 15 solar radii. And on top of that, it was on the back of the sun, the backside of the sun. So we don't really, when this event flew by it, we don't know whether it did something to the spacecraft or not. We had to wait when it emerged on the other side and sent us some telemetry to tell us, everything is fine. So, and by the way, I got you really a lot of data that you will enjoy you will use to understand this type of events. So, okay, this is the event as seen by the imager of Parker Solar Probe. So, okay, what we are seeing here, and by the way, Parker Solar Probe is swinging around the sun here. And when the movie plays again, what we are seeing is this. So we see the normal solar wind, there is nothing there, and all of a sudden, you have this huge structure in front of you. It's so big and so complex. And by the way, Parker Solar Probe was so close that almost immediately it starts flying through it. And it was one of a kind in a way. It's one of the events where we were hoping for to see it. And we got it in September 5th of 2022. And by the way, Parker Solar Probe flew through many of CMEs. This is the biggest one of them, of all of them. Let me. Okay. So what did this do event? What this event did? So it's so big that basically it cleaned everything in front of it. It left nothing. So we understand that the plasma itself, it's easy to clean up because plasma has to stick to the magnetic fields, and the magnetic field will be pushed by the coronal mass ejection. But even the heavy dust particles, these we are talking about very heavy particles, much heavier than the protons and the ions. They were also cleaned out by this event. In a sense, when Parker Solar Probe was flying behind in the wake of the CME, it was flying through a near perfect vacuum. So this event obliterated everything in front of it, except Parker Solar Probe, of course. So when you look at this movie here, and let me restart it from the beginning, and I will step it through it. At the beginning, what you see, okay, you see the CME here. We move a little bit, and we see the wake of the CME around here. And after that, we will see really a dark night here. That the background stars, we can see them so clearly, better than ever before. It's that time when Parker Solar Probe was flying through that vacuum that was created by the passage of the CME. And after that, of course, it takes many hours, something like 18 hours, for the restoration of that medium to get repopulated by dust and by the plasma again. And you will see it toward the end of the movie that it gets brighter again when you see it now getting repopulated again. So okay, let me stop this one. I'll talk about it before, but this is what we did. It's the same event, but what we did the sonification of the magnetic field signal. And that will tell us about the arrival of the shock, the arrival of the CME, and it will give us an idea about the how it looks like if you were riding on Parker Solar Probe during this event. So here, I will let you listen to it first. I'll play it again one more time. So okay, what we are hearing there, we are hearing initially just the background wind, nothing. It's the usual stuff we hear in the solar wind. But all of a sudden, you have that shock wave hitting the spacecraft, and after that, you have the whole CME flying by the spacecraft as well. It's really when we put this on YouTube, I think in something like 5 days, it gathered more than 1 million views, and I'm not sure how many views it has now. So I talked about the coronal heating, the solar wind, the big CMEs and explosions on the sun. But Parker Solar Probe does many other things as well. And one of them is the Geminids, shower that we see in December of each year when we get this meteor shower. And so the Geminids basically come from the trail of an asteroid that is the Phaethon 3200. Here is a direct image of the asteroid itself, but when you look at it, it has a trail of debris along its orbit. And that trail of debris is what created the meteor shower every December. So that's a picture of the Gemini meteor shower. So what Parker Solar Probe does every time during all orbits, we get actually images of this trail here. Okay, the red dashed line is the orbit of Phaethon. But if you look just outside of it, tiny bit outside of it, you will see an excess of emission. That excess of emission is exactly that trail of debris that is reflecting the light of the sun, and you see it there. Okay, we saw it for several orbits. We said, yeah, that's fascinating. It's really something we didn't plan for before, but it's there, and we looked at it. But we got a student at Princeton, his undergrad student, and he had really an eagle eye. And he said, well, you know what? There is something curious about this. Why the emission is always on the outside of the orbit? It's a little bit outside of the orbit. Why doesn't it coincide on the why doesn't it lie on the orbit itself? And well, he started looking into it with some modelers, and then they discovered something that is very original. So this is the trail of the Geminids here as we see it. And there are two scenarios when you are emitting basically this debris. You can emit it, you can release it gradually from the asteroid, or you will have a catastrophic event that you will release it all of a sudden. If it was a gradual release, like in the case of comets, when you have dust and evaporation of organic material in water that is gets slowly away from the coma due to the solar heat. When we do that, we get all that debris to settle down within the orbit itself. It's not in the outside, it's within the orbit. But when we go to the catastrophic case, basically you have an explosion or something like that, the dust will settle, the debris will settle on the outside of the orbit. So basically what this study told us is that sometimes, maybe 2,000, 3,000 years ago, something catastrophic happened to the Phaethon asteroid. And that's actually what created the whole Gemini trail. It's the likelihood is probably an explosion due to excessive heat from the sun, and it is likely happened around here when it was very close to the sun as well. So this is something we did not even expect from Parker Solar Probe, and that is when you go so out of the box, you start thinking so out of the box, and you go really bold with your science, with your engineering, with your technology, with everything. You do a lot of stuff like this that we didn't expect at all. So let me go show a couple of other things. Just give me a second, please. Okay, so I said I'm going to talk a little bit about the TPS, the thermal protection system, or the heat shield. That's actually what enabled the whole mission. Without this, we will not have a mission at all, because that is actually what is standing between the spacecraft and the sun. That is what protected the whole spacecraft. And if you will, okay, let me tell you the story from the beginning, because it's a funny story. So NASA in 2001 commissioned EPL to look into material to be the heat shield for a mission, for a mission, solar probe mission. And it took us something like 6 years to find the material, the right material, and how to build it and everything, fully test it, and we are sure, yeah, that will work. And it's then when NASA moved to confirm, yeah, now we can move forward with implementing the whole mission. Had we failed of finding this material, we will not have Parker Solar Probe. So what is the heat shield? What is it made of? It's basically a piece of carbon foam that is 4.5 inches thick, and it is 2.3 meters wide. And that's basically what it is. There is this white plasma spray on top of it, and it's white for a purpose. We want to reflect as much light that is coming from the sun to deep space as possible. But this is the fascinating thing about it. So when you take the heat shield and You heat it on one side, okay? It will be glowing red. And guess what? You touch it on the backside, you feel absolutely nothing. Well, that is actually the magic of this technology. But when Parker Solar Probe flies closest to the sun on the eve of Christmas 2024, this year, the side of the heat shield, this side here that is facing the sun, will be glowing at more than 2,500 degrees Fahrenheit. The backside, which is just 4.5 inches back, will be at something like 700 degrees. And 1 meter behind, which is about here, we will be at room temperature. And that is actually where the main body of the spacecraft resides and where all the instruments, most of the instruments are functions there. They all work at room temperature, like you and I are sitting in here. Parker Solar Probe, even when it is closest to the sun ever, it is still, the main body of the spacecraft is still at room temperature. Which is fascinating. There is another thing about Parker Solar Probe. Whenever you have a spacecraft there, it will wiggle, it will jitter a tiny bit. For Parker Solar Probe, yeah, it can wiggle a little bit, but the tolerance is a small fraction of a degree. We cannot wiggle by half a degree or a degree. That is, so the TPS has to stay squarely facing the sun all the time. And the way we do it, we have 4 subsystems that control the attitude of the spacecraft all the time. And that keeps it going that way. The other fascinating thing about Parker Solar Probe, and all of this is new technologies that is going into this mission. It's a marvel of technology, by the way. I have always to say that. When Parker Solar Probe is close to the sun, we cannot talk to it. So it has to be 100% autonomous. And whatever problem it might encounter has to deal with it on its own. We cannot do anything to it at all. So we built an autonomy system that can drive the whole spacecraft for up to 2 months without any human intervention at all. And guess what? Whenever Parker Solar Probe encountered an issue, autonomy steps in, solves the issue, keeps the mission going. And that is so fascinating. I think in terms of autonomy, there is no other mission before Parker Solar Probe that has that degree of independence, in a way, autonomy, I would say. And this type of technology will benefit any other space missions we will build in the future. So it is a huge thing. What I want to say by this, developing a mission like Parker Solar Probe open new venues for technology to develop. And that is what we gain also from mission. Let me draw a parallel here with another historical event, that is the moon landing of '69. The moon landing was so historic because, yeah, we put humans on the moon. It's a huge achievement. But guess what? All the technological technological progress we made so far is actually coming from there. That's actually the source of it. So when you go out there and you are so bold, you are opening new venues for new technologies and new things to benefit humanity in general. So I will stop here, and then I'll be happy to answer any questions if you have any. Thank you so much. Do you hear me?
Yes. Okay. Sorry, I was trying to get the mic on. Thank you so very much. Who's got questions?
Hi, Nour. This is Harvey Henson. How are you?
I'm good. Thank you so much.
So when the probe was experiencing that massive CME was it September 22? Did it encounter any plasma or anything close to plasma? Was it?
Yeah, we encountered all sorts of things. I mean, from fields to magnetic fields to electric fields to radio emission to plasma itself. I mean, going from the highest energy particles to the thermal solar wind. We encountered all that sorts of stuff. Yeah, and the other fascinating thing about it as well is the wave activity that comes with this type of events. It's all over the place.
Were there temperature anomalies or did it get that close?
Temperature anomalies in what sense?
Like proximal to plasma or anything close to plasma? Because you talked about the temperature of the plasma.
Yes.
Yeah, was in the millions of degrees, right?
Oh yeah, okay. And now I think you Parker Solar Probe, when it is flying in the solar wind, in the solar corona in particular, it is flying through that multi-million degree hot plasma. Yeah, we are flying through it all the time. But this is the trick. Why one might ask, okay, how comes Parker Solar Probe does not burn when it is flying through that medium? That the solar corona and the solar wind is so tenuous, the densities are so low that it does not transfer much heat to the spacecraft itself. And also Parker Solar Probe does not really, it's so fast, it does not spend too much time there. So it does not get in equilibrium with the plasma itself. So that's why it doesn't. Okay, let me give you the analogy. If you have a hot oven, if you stick your hand into the oven itself, it doesn't, yeah, it feel warm, but it's not that. But if you touch the walls, then it burns. It all has to do about the amount of heat that transfer from the medium to your hand or to your spacecraft in that sense.
Other questions?
Hello.
Hello.
My name is Raiki. Thank you for the great presentations.
Thank you.
I'm from Japan, actually. And then I have questions about the Phaeton's dust trail. And I don't know of the physics or these kind of the spaces kind of things, but I want to ask questions that I heard that the Phaeton's dust trails generated a sodium, but how can they notice that they are generating the sodium, or how can they no?
Okay.
How,
I think the answer to that is like let me first make the analogy to comets, because comets are much easier. We know what they are. So the only thing to know what material there is that the comets are emitting out there is through spectroscopy. We want to analyze the spectrum that is emitted by the material there. And different species, they have specific spectral lines. And once you detect them, you see them, like water, for example. It has specific lines. We know where they are in the spectrum, and we can look for them. Same thing for all the other chemical elements. When they are present, they have their signature on the spectrum. When I started early on by iron-13, we came to know it's iron-13 because it has a very well-known spectrum that now we know it, very well-known spectrum. And one of the lines is the green line. Same thing for the Gemini trail. When you look at the spectrum emitted by the trail itself, you can figure out what are the chemical elements present there. And sodium is one of them, because we are seeing the typical lines, spectral lines that are emitted by sodium.
thank you so much.
You're welcome.
Has Parker Solar Probe detected any comets?
Oh, yes. Oh, yeah, we detected a few of them. Yes. And we saw them. Unfortunately, I don't have the movie with me here, but one of them is so fascinating. You see the comets coming from very far away. And it is, yeah, you see the typical thing. And all of a sudden, you see it accelerating toward the sun. And guess what? That's not really the comet that is accelerating. Actually, what we are seeing the combination of the speed of the comet with the speed of the spacecraft. So the spacecraft is going so fast around the sun that you are basically seeing the comet like it's going, falling toward the sun, but it's just apparent speed. That's what it is. But we saw several of them, definitely, yes.
Do we have any other questions?
Let me say one thing.
Go ahead.
The thing that I hope we will never do with Parker Solar Probe. So we know whenever there are comets, they leave a dust trail behind them. I hope that Parker Solar Probe will never fly through one of these tails of dust, because that will be, I think it will do few bad things to the spacecraft, and we don't want that, definitely.
We have one question from someone who's joining us online. They said, if you could know what causes the acceleration of solar particles and what's happening in magnetic reversals,
Yes.
what can it help us answer?
Okay. This is really a fascinating question, and it's so deep. In a way, okay, please allow me to translate the question in a different way. So basically, in a way, what you are asking me, yeah, okay, we're doing all this fascinating science and all that. So what is it good for? What does it do to us here? So let me start with the science. And as a scientist, I'm very curious. I want to understand, and I'll be happy to tell you if I understand the solar wind, that's the happiest day of my life. And that will be just enough for me. But for everybody out there, yeah, we invest into these space missions. We try to understand what is going on there. Let me tell you the first answer. First of all, we live in that flow of the solar wind, and when the sun is active and is launching these flares and CMEs, actually they impact us. And if you see the movie of the 40 spacecrafts from SpaceX, that's actually the effect of one of these events on the sun. I can show you the movie from the blackouts in 1989, where a huge region on the northeast of the US and Canada lost power for many hours. Imagine that we get a huge event like the Carrington event in 1869, and it hits us here on Earth. And you have a blackout all over the place for an extended period of time. Can you imagine what is the amount of the level of losses in terms of economic losses? The estimates is something north of $3 trillion. That's the cost. And on top of that, I talked about having women and men out there on the moon and maybe in deep space as a permanent presence there. That's another thing. But let me touch about something else that we really don't talk much about it. So what we are studying with Parker Solar Probe and other missions, we are looking at the variability of the sun, a short-term variability of the sun as a star. But when you look at the past of the sun, there is another type of variability that is long-term variability. And this has a period of something between 100 to 200 years. And every 200 years, basically the sun goes very dim, very quiet. And the Maunder minimum that occurred in the 1700s is one of these periods. And what these events cause is basically mini ice age. And when you talk about mini ice age, we are talking about our lives. You know, it can lock energy sources. It can affect our crops, basically our food, what we eat. It can actually cause mass motions of people around the globe. So it will affect our daily lives. And that is exactly why we need to understand the sun as a star. You know what? We know that the sun is the most important star to us in the whole universe. You can talk about, this black hole there, this thing there. But to us, to our daily lives, there is nothing more important than the sun. And let me start with the easiest thing. If the sun is not there for a long time and it's cloudy and it's, gray and all that, our mood is not really that good. When the sun shows up, oh my goodness, wow, this is fantastic. But it goes to more things. Our food actually needs the sun to grow. So that's the easiest thing. But now we have to look at the future, what's going to happen with this star that we cannot live without. And that's what we are looking for. So this fundamental research, it has to pay off. When you know your stars that well, you can actually deal with it, deal with the consequences later on. There is another thing that we often do not talk about. I mean, when you look at climate change here, it's so evident now, we see it. If the sun enters one of these periods of tranquility, I don't think we scientists don't think that will reverse the effect of global warming completely. But actually, it might slow it down a tiny bit. It will help us. We don't know. That does not mean that we should not take action now. We should. But you never know. If that happens, it might actually help us. So in a way, understanding the sun is for our own benefit. And I cannot say it more. The sun is the most important star to us ever.
Thank you so very much. Can we please thank Dr. Rawafi for his time?
Thank you. Thank you. It's really a pleasure. Thank you.
Thank you for joining us. And we're all going to pay attention December 24th, right? Most important day for Parker Solar Probe.
Thank you. It's the most important day for all humanity. It's really a huge achievement for all humanity. It's not only for the Parker Solar Probe team.
A couple reminders. We have one more talk for the Eclipse series on April 5th. That'll be Lou Mayo talking 3 o'clock, same room. Don't forget, April 8th, total solar eclipse. That whole weekend, there are events all across campus, all across Carbondale. Most of them are free. Invite your friends, invite your guests. There are also tons of amazing volunteer opportunities if you want to get involved in the eclipse. If you go to eclipse.siu.edu, all the events are there. There's volunteer opportunities. We need help. If you want to get into the stadium show, the Comic-Con, like all these cool, fun things. We're going to have telescopes out. We're going to have a planetarium out. All sorts of opportunities, not only to see, but to get your hands on and get involved. So check out the volunteer page and join us for the eclipse. Oh, hold on. One more. What do you got? Yeah, so grab an eclipse sticker before you go. All right, thank you everyone for coming. Thank you so much for joining us and taking time for us.
It's really a pleasure. Thank you.